I'm Kovas Boguta. Thank you so much for coming. I'm excited to talk to you about Gamma. Gamma is a Clojure script library for WebGL with an emphasis on composition and simplicity. I'm going to show Gamma, demo some stuff. This is also an ideas talk, regardless what programming language you use, whether you even use WebGL. I hope that this talk gives people some ideas for the next time they confront a domain in which composition seems to be difficult to get to. So we're going to start off talking at a very high level about the problem that Gamma is trying to solve. Then we'll pop open the hood on WebGL and take a deeper look at the causes and consequences of that problem. Then we'll move into the solution that Gamma embodies and do some demos. So the problem. Gamma is, graphics programming is a little bit more extreme than some other domains in this need to experiment and iterate. And that's basically two reasons. One, the result is subjective. Does it look good? Varies from application to application. To know if it looks good, you actually have to do the experiment. There's no kind of shortcut to that. And you also need to iterate quite a bit because the solution space is just vast. Just graphics is always evolving. Countless methods that keep evolving. The developer has to contend with a very big solution space that they need to iterate through to get to the trade-off point of performance and quality that they're looking for their application. Now, computer science, software engineering, there's this huge body about abstraction and reuse that is intended to let us iterate quickly, right? But let's face it, in graphics programming, the promise of these tools does not match the reality. Graphics programming is like 2001, except you get to choose which monolith you spend the rest of your life with, right? Like, the field is completely dominated by graphics engines. And these things do everything behind that nice, beautiful exterior. It's like shaders, state management, optimization algorithms, 3D math, asset loading. And as long as what you're experimenting and iterating on remains within the bounds of the monolith, you're good. But as soon as you want to do something fundamentally new, some actual experiment, and you need to do some actual graphics programming, it's sort of like you're back to banging bones on bones because there's not an ecosystem of small composable libraries that you can lean on when you just want to remix things in a different way. That's really the fundamental problem I'm trying to get at with Gamma is this lack of composition at the bottom of graphics. There's one thing I want people to take away is that composition in graphics is an unsolved problem. And it's an important problem, not because if we solve it, the existing players will benefit, but if we can solve composition, this will open the door to graphics, to the broader world of programming. All these people who are interested in graphics want to get into graphics, but they can't because when they look in the field, they see this alien universe where the normal laws of the universe don't apply. Instead of using their higher order functions or monads or whatever, it's like, let's just pile if statements on top of each other. So we want to fix the composition problem to make graphics programming more accessible, more productive, and easier to experiment with. All right, so let's pop the hood open on WebGL and see exactly where the problem is coming from and what the consequences are. For the uninitiated toy model of WebGL, there's the CPU and there's the GPU. CPU does two things. It puts in a shader program in the GPU and it puts data into the GPU memory. GPU runs, data flows to the shader. This creates pixels. Pixels go in this thing called the frame buffer, which is either blitted to the screen or recycled as data for another pass. So these two things, the shader program and the process of putting the data on the GPU, are sort of the two fundamental sources of complexity that thwart composition. And these are the things that we're going to try to fix. But let's take a closer look at them first. So shaders. Shaders, as many of you know, are written in a language called GLSL. GLSL is extremely primitive. It pretty much thwarts composition at every turn. Almost nothing in the way of data structures, almost nothing in the way of polymorphism. You notice no import statement. There's no sort of standard way to have some library of functions and just kind of import functions into your shader. Input and output is done through global variables. There's no way to pass functionality into the shader, and there's no way for the shader to delegate functionality to somebody else. Really primitive stuff. And if you're writing one shader, maybe that's OK. But an application, you might need dozens of shaders doing different things. And those shaders are going to share logic. In an ideal world, we'd want something like this, right? We want some new shader, say we're going to call it F. We have some existing pieces lying around called G and H that each do part of the job. We're just going to stack those together and get our new shader, right? Unfortunately, this is not how it works. There's just not enough there in the realm of shaders to let you programmatically compose shaders into new shaders, or programmatically compose their pieces into new shaders. But people need to do this, so what do? So there's a variety of approaches. By far the most common is to say, okay, we're going to have a bunch of shader fragments, maybe as files on disk or something, and they're each going to do some part of the job. And for a given task or for a given shader, we're going to pick the fragments that we want and just string join it all together, right? Just mash it all up. And this might be expedient, right? But this is not composition. It's not composition if you have to plan in advance so that assumptions can line up in the future. And this kind of non-compositional or pre-compositional state has real consequences for product development. It's hard to improve the system if to make some improvement, you have to figure out how to squeeze it into the web of assumptions and then make sure nothing breaks. It's hard to prototype if you have to plan in advance which variations you want to try. And perhaps more subtly, the first idea tends to get set in stone. So I started building my system. I had an idea for some artisanal shader factoring strategy. A year or two goes by, and we realize this is not the right way to do things, but now this thing is just like too hard to move. There's too many intertwinings. And that first idea I had was set in stone, and I can't move on to the right idea. So in a bad place with regards to shaders. Second thing, this thing of setting the GL state, which I rather optimistically depicted as the CPU just putting data into the GPU. Well, one does not simply set the GL state, right? Because you're not just setting the state, it's the whole state machine. I love this slide. The OpenGL machine, complicated from inception. And it really is. It's like, okay, I need to set a piece of state over here, but first I need to set a piece of state over here. And if you're doing textures, you have to set a piece of state over here, to set a piece of state over here, set a piece of state over here. It's a real Rube Goldberg machine. And if your code is manipulating that state machine, your code becomes a Rube Goldberg machine. And this is not something you can just factor out, right? Okay, you have these operations, you split them up into functions and methods or whatever. Now you have two problems. You have the problem of the state machine, which is still there. Your code still needs to comply with the Rube Goldberg invariant. And now you have whatever other weird abstraction you put on top of that you have to chase around and manage. So this is real kryptonite for composition with the same problems that I talked about just a minute ago. And putting it all together, we can begin to see sort of the architectural consequences that permeate the field. So you have these unmitigated sources of complexity at the bottom that are never really solved. And then all you can really do is add assumptions at every layer in the software. So you can't precisely describe which shaders you want through composition, so the layer above the shaders has to make assumptions about what the shaders are. And it basically exposes a slightly less big surface area API to the layer above that. That person adds some more assumptions, exposes a little bit less surface area to the layer above that, and so forth until you get to the user API, which appears to have a small surface area, but in reality is completely constrained by this tower of assumptions underneath it, right? So if the user wants to do something a little bit different, they have to unwind these assumptions potentially all the way down to the bottom and squeeze their thing in. Obviously, interoperability is not going to happen. You have your other assumption pyramid over here, and these things are just not going to line up, right? This is how monoliths grow. So to solve the problem, we need to solve the problem at the bottom with shaders and state. So let's do this, gamma. The basic idea here is the minimum composable system. We're not shipping asset management. We're not shipping 3D geometry libraries, none of that stuff. The only thing we care about is taking the WebGL API and making the smallest possible change to it to recover the property of composition. We want to make as few assumptions as possible so that Gamma provides an awesome platform for you to build your own graphics abstractions. And we want to place the fewest possible constraints on what those abstractions can be. the basic strategy we're going to use is we're going to meet on data. So we're going to take those low-level APIs, make very small changes to them so that we can represent them as composable data. There's basically compilers that take that data and convert them back down to the actual API. But as far as the user concerned, the only thing they now need to do is to generate data. And this is like the easiest thing ever, right? Like, you can generate it yourself. You can use libraries to generate it. You can stack the libraries on top of each other. You can call into any level of this chain of abstractions you want. Constructor functions generating data is a very, very good place to be in terms of composition. So let's go into shaders. As I alluded to, we're going to represent the GLSL AST as data. And we're going to use vanilla Clojure programming to build up that AST, which means we get to inherit all the compositional properties of Clojure, right? Functions, multi-methods, protocols, all these data structures, whatever. Clojure has compositional mechanisms, we get to use them. And we're going to compile that to GLSL. Now, the discerning listener will be like, this sounds like metaprogramming. Like, but isn't metaprogramming like the least simple and least compositional thing we could imagine? This doesn't sound like vanilla programming. Well, it turns out that the simplicity of GLSL actually comes to our rescue here, because we can sort of constrain our thing to a form of metaprogramming that doesn't suck. In particular, once you get rid of things like variables and scoping and assignments, mutability, if you get rid of those, metaprogramming actually becomes extremely easy and simple. And the reason why we can get rid of those is because shaders are actually functions. They're actually almost entirely pure functions, which means that the thing that the shader computes can be semantically represented by a referentially transparent expression. Right? Any value can be replaced with the expression that computes it and vice versa. And this means that we don't need intermediary variables. We don't need mutability or assignments, any of that stuff. We can just pass these AST fragments around, proliferating them to where they need to go, and lean on the compiler to factor them out at the end of the day. Right? So this is a little bit abstract, so we're just going to jump into the demo, and I'll show you how this works. But the bottom line is metaprogramming becomes like normal programming. All right, enough talking. Let's do some demo. OK, great. OK, so my first shader. So as I mentioned, we're going to represent, let's see here. We can, OK, I think that's good. We're going to represent the shader as data. Now, it's a little bit inconvenient to just type in raw data structures all the time. So the primary API is constructor functions. If we want a GLSL attribute variable, we have an attribute function. We pass the name, we pass the type, and what we get back is a hash map representing as data a GLSL attribute variable. Likewise, shaders are represented as data. We have a triangle shader. It's a hash map. It has vertex shader and it has a fragment shader. Each one of those shaders is represented, again, by a hash map whose keys represent one of the outputs of the shader. A shader can have multiple outputs. And the value is the AST fragment, which, when it runs, gets assigned to that output. So the vertex shader is simply going to take the attribute and pass it along as the output to the built-in GL position variable. And the fragment shader is just going to take the constant red and assign it to the built-in GL frag output, which sets the color of the thing. So we have our shader here. It's, again, just a big data structure. We compile the shader, and then we can ask to see the actual GLSL string. So the vertex shader looks like this. We have our attribute declaration, main void, and we're just assigning the GL position to the attribute position thing. Likewise, the fragment shader, pretty simple. We just assign the spec4 to the frag color. Then we can run the thing. And woohoo, we see a red triangle. We can change this coordinate a little bit just to prove that it's responding to what we're telling it to. So basic draw is a utility function that I'm going to explain in the next part of the talk, but for the purposes right now, it just lets us draw the shaders that we're constructing with some input data. Okay, so we have our first shader. Now we want to build abstractions and start composing stuff. So one of the nicest mechanisms of composition is the function. Instead of hard coding the position attribute and the color, as we were in the previous shader, we're just going to pass those as arguments to a function which will construct a brand new shader for us. So the shader is going to consume as its argument a hash map with the keys position and color. And those things are just going to get passed into these positions in the shader. So we have our thing, we have our shader function, and this is actually not what I wanted to show right here. Let's just grab this guy. Yeah. Okay. And we're just going to print out this thing. Okay. Okay, so now we're calling the shader function with our parameters for the color and position. We compile it, and then we print out the GLSL. Right? So instead of pre-baking these attributes and the color, we're passing it in. So if for some reason we need to change the name of the thing, we just change the name of the thing that we're passing down the pipeline, right? So we change the name of the thing, and we see the name of the thing has changed. Also, there's absolutely no constraint that this thing just needs to be a constant value. We can just start putting any kind of GLSL AST we want in that position. So, okay, forget constants. We are going to instead, for some reason we decided that we're going to use a uniform, the color, and this is like vec3, right? We pass a uniform instead, and now in our code, a uniform declaration appears, color is in there, we're happy. We can start building up bigger bits of AST fragments, so we're going to say GBR or something, the swizzle operation, just some simple computation. So we parameterize our shader, and now we can just start passing program fragments that we built up however we want into the thing, and we can get a new shader. That's pretty good compared to squashing strings together. Okay, so for the rest of this talk, or for the rest of this part of the demo, I'm going to use a particular shader skeleton that's just going to allow us to quickly explore coloring every pixel on the canvas. So what we're going to want to do is, in particular, we want to color the pixel according to some formula involving the XY position of the pixel. And so something like this, for example. So what we're going to do is, we need to normalize. First, we're going to pop, say, the X coordinate out of the GL frag coord built in. And we're going to divide that by the width, because GL frag coordinate basically scales, in this case, from 0 to 512. And we want to rescale it to be between 0 and 1, so we have a consistent basis on which to build further operations. So we rescale X, we rescale Y. We return a Clojure data structure to contain those two AST fragments. We use a normal Clojure binding form to destructure those two AST fragments out of there. And then we pass them into the thing that's going to generate the vec3, which will represent the RGB values of the color that we want. Okay, so that's cool. But let's make something a little bit more interesting. So we're going to have another function, the dots function. And what this is going to do for us is it's going to compute these two combinations of sine x times cosine y and cosine x times sine of y. Again, drop them into a data structure. And then we use a higher order function, map, Clojure script higher order function. We're going to map the absolute value constructor function across those two things, because sine and cosine vary from -1 to 1, but our colors only go from 0 to 1. So we map the absolute value on there. We get a Clojure script sequence. So start with normalized coordinates, call dots, destructure the result, again, pass it into our thing. I should probably evaluate this thing first. Okay. Now, this doesn't do anything that interesting because we're just going from 0 to 1 still. We're not seeing the repeated behavior of the thing. So we'll have another little helper function to rescale after we normalize from 0 to 1, we're going to rescale it to go up to 50. And now we see why we call it the dots function. Oh, yeah. Okay. So that's kind of neat. Now the grizzled GLSL warrior will point out that why not just use the vectorized GLSL functions? It's cool that you do this higher order stuff. Just use like ClojureScript destructuring, but this is kind of overkill. And they would be right. This is kind of overkill for this particular example. But I'm doing it this way because I want to show you one other thing, which is let's take a look at the source code. Let's take a look at the source code that's generated by this example. Okay, so what we have here is, so this is the normalized and rescaled x coordinate. This is the normalized and rescaled y coordinate. And then we're reusing both of those things in these two variations of sine and cosine. Okay, so what happens if we drop g from the result? Well, we drop g from the code, right? Like we're not using it. There's no need to include it in the code. This is dead code elimination. And what this means is your helper functions do not have to care about how they're used by the shaders above it. So they can return a bunch of results. You can have some infinite sequence of like shaders being generated by some helper function. And only the stuff that you use will end up being encoded into the compiled shader. Another thing that happens is, okay, let's say we use R twice. What's going to happen? So if we use R twice, it's in fact going to detect that and insert an intermediary variable to just contain the value of R, and then we include that value twice in the output. So this is common sub-expression elimination. And this is actually the key thing to getting this thing to work, right? This is, right, it's like, what's the result? What's the result of this? Just this dots function, right? It's like, this huge pile of like AST stuff. But what we want to do, we want to pretend it's a value, use something like a let, some binding form, and then replicate it to wherever we understand that that value is going to be needed. And because we're doing common sub-expression elimination, this all works out because the compiler will then notice it's happening multiple places and just do the transformation necessary to make this a plausible thing. Okay, so let's move on to some more interesting visual result here. We can make a circle function. So pass the coordinates of the fragment, pass the center coordinates of the circle and the radius, and it'll just return 1 or 0 depending on if the thing is inside or outside of the circle. That's cool, but it's a little bit more interesting if we map basically the circle across our dots function. So we're going to say the center of the circle and the radius is going to come from the dots function. And now we have something a little bit more interesting. And as sort of a final demo of this section, we can make a couple more tweaks and get a somewhat interesting animated shader that does something non-trivial and somewhat pleasing, depending on your point of view. So, okay, yes, thank you. All right, so where have we landed here? Okay, instead of a artisanal system, our method of composition and abstraction is called ClojureScript. It's pretty good. You should check it out. We can easily define reusable bits of logic and stack them together to explore the design space. We don't need to make assumptions because we can just put parameters in at the top and let them flow through the system. And sort of just as a programmer ergonomics point of view and a reasoning point of view, we're manipulating programs as if we're just manipulating values. It really is quite simple, intuitive, and easy. So we're in a much better place with respect to shaders now. Somewhat more challenging scenario, composing these state operations. Oh dear, let's do it. So we're gonna do 3 moves that basically get us to a better place. We're gonna reify all this global implicit state into a package that we can explicitly pass around. We're going to specify the configuration aspect of that state, which is sort of the wiring or the plumbing of how the objects relate to each other. That's going to be immutable data. And that's going to be kind of the core of how this all works. And finally, we're going to need to operate against the model of GPU state. I mean, it's insane to try to operate directly against the GPU. We need sort of an intermediary which keeps track of what we've done to the GPU so far. And when we put in a new specification, it's going to conform the GPU to whatever state we specified based on wherever it's at the moment. So the low-level API is something like this. You might want to do something like draw arrays. It takes 3 arguments. This looks pretty easy, right? Well, in fact, there's an enormous pile of implicit state hiding behind that very simple call. You have to set the program. Have to set the frame buffer. Have to set which vertex attributes point to which array buffers, and there could be a bunch of them. You have to set all the uniforms. If you're using textures, you have to bind the texture. If you want to bind the texture, you have to set the active texture. There's just this huge pile of implicit state. So what we're going to do is we're going to take this pile of implicit state, reify it into a concrete object, and pass it directly as an argument to our draw arrays call. So what this means is different draw array calls are no longer going to have an opportunity to step on each other. It's just no longer possible, right? You have all the information you need right there, and if you need to add another operation sort of in the middle of the sequence or at the end, no one's the wiser. Next thing we're going to do is, if you look at the state, there's actually 2 kinds of state. There's the state that the shader program actually sees, sort of the data in the array buffers or the data in the textures and the uniforms and so forth. And then there's just this pile of plumbing information. What texture unit is bound to which texture? Which array buffer is bound to which attribute? What's the current frame buffer? What texture is that frame buffer connected to? What render buffer is that texture that frame buffer connected to? Just like all this wiring information. And this part we want to specify is immutable data. So the situation that we want is the configuration is immutable. You might have a few of these configurations. They're immutable. They never change. And then you have data that's flowing through them, which is sort of the runtime data for the shader. So we can call out to these different configurations without them stepping on each other while passing the different runtime values into the shader program. But we still need a way to execute this GPU plumbing. And that's where the model comes in. I don't have a lot of time to get into the details of the model, but point being, everybody ends up needing a model of the GPU state because the GPU is a black hole. You can't kind of ask it what its state is and expect to perform. So we modeled the GPU, and we expose a data-oriented interface to it so that no one who writes code against the Gamma API ever has to deal with runtime objects that contain or expose GPU state directly. This is sort of how we prevent the contagion. So kind of the resulting picture is something like this. We have a draw arrays constructor. We pass the model. We pass the GPU plumbing specification. And this compiles down to a draw arrays object. We call exec, that's part of the API, with the runtime shader data, and something actually happens. Now, sort of a subtle but important point here is in the process of draw arrays running its constructor and creating this object, this is our opportunity to sort of pre-compile, pre-optimize, initialize, allocate, et cetera, because we don't want to pay the price of transforming this immutable data specification, which isn't going to change over and over and over again with every draw call. We want to have an opportunity to just unroll it once, set up some very efficient non-allocating operations that cause that state to happen, and just be able to call it quickly over and over again. So that's sort of the setup there. And how the API ends up shaking out is you have a bunch of data constructors, which are similar to the GLSL stuff. They just generate data. You're not containing any runtime objects in there. And then you have these operations, which are also which involve specifications involving the data constructors, but when executed will end up changing the state. So the bottom line is no more hidden state, no more interactions. The specification can be abstracted using simple data. And we're agnostic to data formats, caching strategies, et cetera, by way of the pluggable model. And that will let you hit these different positions in the trade-off space. So let's show a little bit about how that works. OK, yes. So what we want to do is first I'm going to show you. So I'm going to show you how this basic draw function works, and then we'll move into a slightly higher order demo. So the purpose of basic draw is to consume some shader that we just constructed and just provide us something that can draw, actually execute and draw it to the screen using some very simple conventions. So I'm not going to step through every line here, but the point of this is this function saves you a ton of boilerplate, but it itself remains transparent. So if any of you have seen these sort of like WebGL tutorials online, it's like the first thing you'll notice is no one's using the actual WebGL API. Everyone has a bunch of helper functions that like wire up a bunch of stuff. And then you're like looking at this tutorial, but you're trying to understand what's happening, but it's like all mutable, and it's like, do I need to call this one first, or do I need to call that one first? Like, what order can I call them in? How do I add something in? Like, what's built in, what's not built in? Like, what's the convention here? So this function, however, is based only on transforming immutable data, so it's very easy to just pop it open and understand what the data flow is and change that data flow if you need to. So just to kind of walk through here a little bit, so we can get the inputs from the shader and get all the attributes on that shader. For every attribute, we're going to create an array buffer, and we're going to turn that into a hash map of sort of attributes to array buffers. For each array buffer, we also want to construct an operation that will allow us to put data into that array buffer. And then we construct the draw arrays call. So we get the model, the program, and the frame buffer from above. And then all we need to do is to create this specification of how to wire the attributes up. So the attribute wiring specification is basically we want to say the name of the attribute, and we want to tell it which array buffer to use and what layout to use. And the layout looks something like this. It's like these, all these parameters that you have to pass into the API about sort of where in the array buffer to find the attribute. And in basic draw, we're just making the assumption that there's going to be a one-to-one relationship between attributes and frame buffers. So this is just a very simple scenario. But if you want to make a more complicated topology, I mean, it's all the same principles. You just figure out what you want, pass it into the right places, and call it a day. When it comes time to execute the thing, so we've closed over draw arrays, we've closed over a bunch of these buffer data calls. So we just pluck by attribute name data out of the argument, stuff it into the buffer datas, and we also call the draw that we've constructed. And that's it. Not very complicated. So let's show you something a little bit different. So the place where we want to be is in this namespace. Let's see here. OK. So we can continue this process as sort of constructor-based wiring of your graphics pipeline up to a higher level. So what I've done here is I have encapsulated this interesting shader that we made into a construct implementing exec. And I also have, on the side, have created another program that just draws a cube, and that thing that draws a cube expects a texture. And we're going to wire these two things up together via a frame buffer. So we have a sort of frame buffer constructor function. Given a width and a height, it constructs a frame buffer with a certain kind of texture at the color attachment and a certain kind of render buffer at the depth attachment. So we can evaluate this and just show you what that looks like. And then we can pluck the texture out of that frame buffer and combine it with the texture unit, since most accesses to texture have to go through a texture unit. And then we make something that initializes the texture, and then we make something that we're gonna draw the fancy shader to a frame buffer, which means it's not gonna be drawn to the screen. And then we're gonna draw the cube with the texture coming from that frame buffer. And that's basically this bit right here. So if I were to say, change this parameter, yeah, okay. Yes, a cube with that thing as the texture. So, this, yeah, okay. So let's just animate this thing, and okay. So this is pretty cool, right? We can just like take things that we defined ahead of time. These things do not know anything about each other, and then for them to interact, we construct some stuff at the next level up and just pass that into those two things. So this is a very easy data flow to think about, as opposed to like someone in the distant past constructed this object, and now I'm going to bang on it so that sometime in the distant future, somebody else can pick that thing up and have its values be there. So this is composition. I mean, I think that there are some parts of the system that the design is still a little bit up in the air, but the general principle of saying we're going to do the configuration as data and then just kind of pass all this stuff down through the system while allowing opportunities for optimization and parameterization and plugging in sort of these very specific, application-specific details, I think is a powerful way to go. So that's it. I am Kovas B on Twitter, kovas.boguta@gmail.com. Check out my GitHub. I'll be posting most of this code probably over the weekend. And a lot of these talks finish with, we're hiring. I'm actually looking for gigs, so if anyone's interested, don't be shy. Thank you very much.